here's a medium level torque problem. So say you have a stick and the stick has length L and you've suspended it by a string in the center. And you hang a mass M1 over on one end of the stick. And you want to know where should you attach M2 so that this whole thing is balanced and the stick is level. Okay, so this is a statics problem because we want this thing to be totally level, so we don't want it to rotate and we don't want it to move. So statics tells us that the sum of the torque is 0 and the sum of the force is 0. Okay, so let's just attach M2 at a point. So let's attach it here, and let's call this distance D. So D is what we're looking for. We want to know where should we attach this mass so that this balances. So we want to know D. And we can solve for that in terms of L and the two masses and relevant physical constants. Okay, so when you're starting a torque problem or any statics problem, I always start with the torque equation because sometimes that's the only one you need. So let's start with summing the torque, setting it equal to 0. So the first step is to draw an extended free body diagram where you identify the object. So our object is the stick, and then we draw a free body diagram with all the forces located where they're acting. So over here, this mass M1 is pulling down on the stick. So this is the force from mass 1. Over here we have the force pulling down from mass 2. And then the stick has some mass, so there's gravity pulling on the center of mass of the stick, and there's a tension force pulling up from the string. So we have 4 forces. 1, 2, 3, 4. Okay, so we've drawn our free body diagram. Now we need to pick our pivot. So we don't know anything about the tension and we don't know anything about the mass of the stick. So I'm going to pick my pivot to be the point where the string is attached so that those two forces don't contribute anything to the torque. And we'll see why they don't contribute anything to the torque in a second. Okay, so when I'm summing the torque, I like to just put the sign in as I write. So we're going to say that if a force is going to move the stick clockwise, that torque is negative, and if it's going to move the stick counterclockwise, that torque is positive. So is this a positive or a negative torque? Well, if we pull down on it, the whole stick is going to rotate clockwise, so that should be a negative torque. So negative torque from force 1, and then these are not going to contribute any torque because the distance from the pivot is 0. But this is going to exert a torque because there's a distance between these 2 points. So is this force going to give us a positive or a negative torque? Well, if we pull down on this force, it's going to rotate it in the positive direction, so we need to add the torque at point 2. Okay, so that tells us that the torque point 1 is equal to the torque at point 2. So what's the torque at point 1? Well, we know that torque is R F sine theta. So we already took care of the sine. We know if this is plus or minus. What's the angle between R and F? Well, the R goes from the pivot to the point where the force is applied. So this is our R, and the force vector points down like this. So there's a 90-degree angle between those two vectors. So the sine here should be 90 degrees. But the sine of 90 degrees is 1. So that means that the torque at point 1 is that distance r, which in our case is L over 2, times the force, F1, and our angle is 90 degrees, so the sine theta is 1. So we're done. Now how about torque 2? So torque 2 is a distance, so we need to know what's this distance right here. What is this r? Well, that's L over 2 minus d. And that force is F2. Okay, so what are F1 and F2? Well, these are both hanging here under the influence of gravity. So this force, there's no other forces in the y direction there, so the tension in the string is the same as the weight of the box. So F1 is going to be m1g, and F2 is going to be m2g. So the g's will cancel, and now all that's left to do is solve for this distance that we want. So let's do that. I'm going to continue it over here. So I'll just distribute L over 2. Actually, you know what? I'll start by dividing both sides by m2. So I'll divide this side by m2, and I'll divide this side by m2. So that gives us L over 2 m1 over m2, and that's got to be equal to L over 2 minus d. So I'm going to move d over to this side, so I'll have plus d, and I'll move this over to the other side. So we'll still have our L over 2, and then we'll be subtracting L over 2 m1 over m2. So now, just for fun, I'm going to pull L over 2 out of this. So we have d is L over 2 times 1 minus m1 over m2. So that's our final equation. So now we can look at it and see if it makes sense. So if these two masses were the same, so suppose m1 was equal to m2, and let's just call that m. So if they were the same, how far would you expect m2 to be placed so that this would balance? Well, you know from experience that if you have something with mass and you put your finger in the middle, you can balance it. So you would expect this distance to be L over 2. So let's see if when this is true, does d equal L over 2? So if we use our equation here, d is L over 2 times 1 minus m over m. Oh, no, we wouldn't want d to be L over 2. We would want d to be 0 because d was measured from the end, right? D was measured from the end. So if m2 was at the end of the stick, d would be 0. So this is just, that was silly. Okay. But if m1 is equal to m2, then this is 1 and this is 0, and then we get d equals 0. So assuming you didn't mess that up like I did, well, I suppose I figured it out, this would give you some inkling that what you're doing is correct.